We all accept c squared in physics equations. But what does that squared velocity actually look like in physical space? To see it, let's track a single infrared photon traveling through a vacuum. In Mathis's model, this photon has two separate motions. First, it shoots straight forward at the speed of light, c. But simultaneously, the particle is spinning, tracing a microscopic local loop as it rotates. Here's the friction. That spin wavelength is incredibly tiny, but the infrared light waves we actually measure are huge, 8 micrometers long. How does a tiny spin create a giant wave? The massive forward speed physically stretches those tight spinning loops, pulling them apart into a long, undulating path through space. The scaling factor that turns that tiny spin into a massive wave is exactly c squared. It's the mechanical ratio between the photon's two vectors of motion, which means the photon isn't a particle carrying a wave. The spinning particle's stretched motion is the wave. And that massive 8 micrometer infrared heat wave you measure in the lab, it is entirely created by the photon's tiny spinning motion, physically stretched across space by a factor of c squared.